All right, the last characteristic of functions we're going to talk about is whether a function is even or odd. And this can tell us a lot about the symmetry of the graph and basically maybe what the basic shape looks like. So a few notes to copy down there. We're going to talk about two quick tests. We're first going to talk about the algebraic test to determine whether or not a function is even or odd. And you see there's some notation there. We're going to sub in negative x in for x everywhere in the function and then analyze the results. So if the function is even, so when we sub in a negative x into the function, it's actually going to give us the end result, the function we started with in the first place. This will make a lot more sense, I think, when we look at some basic examples. So pause if you need to, if you're still copying notes. But I first want to look at an example of a really basic even function. So here's our example, f of x equals x squared. So again, the algebraic test is we're subbing in negative x everywhere in the function. So we're going to start by subbing in a negative x right here in the original function. And then again, right here on the other side. So there's no real math to do on the left-hand side, so I'm just going to bring down f of negative x. But on this other side, what happens when you square anything? Or in this case, what happens when you square a negative value? A negative value times itself is always going to give you a positive value. So negative x squared is actually ends up being positive x squared. And you'll see that is what we started with. At the very beginning, the original function f of x was equal to x squared. Well, so is when we sub in a negative x. So f of negative x and f of x, therefore, are the same thing when we plug in a negative x for x squared. So now let's look at a basic example of an odd function. So here's our basic example, f of x equals x cubed. We're going to sub in a negative x. Now here, a negative times a negative times a negative, because we're cubing negative x, is still a negative x. So this end result is a negative 1 times x to the third. Because when you cube a negative number, it stays negative. So essentially, we're just tacking on a negative value right here up front in the original function. And that is the definition of an odd function. When you sub in a negative x, and it basically just makes the function opposite of what it is. And of course, common sense says if neither of the above is true, then it's neither even or odd. So let's finish with a couple more basic algebraic examples. And here should be the directions, whether or not the function is even, odd, or neither. So let's start by subbing in a negative for x. And really the same thing happens that happened in the previous example. If you square a negative number, you end up with a positive number. So negative x squared is positive x squared. Of course, nothing happens to the minus 4. So you'll notice the end result is the same thing as the beginning function. So this function is considered an even function. And here in a second, we're going to talk about what that means for the graph of the function. Letter B, sub in negative x. This time we have two places where we can sub it in at. And again, we're going to get a negative x cubed, and then a negative 2 times a negative x is a positive 2x. And you can see pretty quickly that both of these terms are opposite. So that originally was a positive x cubed. Now we've got a negative x cubed. This is a negative 2x. That's a positive 2x. Now the technical algebraic way to do this is to factor out a negative 1. And then when you factor out that negative 1, you can see that our end result is the exact opposite of the original function. So since it's the exact opposite, this is an odd function. I don't really have space to put it anywhere, so I'll just put it here. So letter B is an odd function. Try to go ahead and start that last one, letter C, see what you come up with. So we end up with this when we plug in negative x. You get positive x squared, you get a positive 3x, and 4 is positive as well. So the question is, there's nothing really, we can't factor anything out here since all the terms are positive. Question is, first off, we know it's not even. For it to be even, it's got to be exactly the same as this original function. It's not exactly the same. Are all the terms opposite? Well, x squared is positive here, and it's positive here, so we're good there. Those aren't opposites, and that's what odd functions are. The only term that's actually opposite is negative 3x and positive 3x. So this one's not odd, this one's not even, so we're just going to say neither. So you'll see a lot of the times when the exponent is a 2, when the largest exponent is a 4 or a 6, a lot of times it ends up being even. But we saw here in choice in problem C that it's not always the case. All right, then finally, even and odd functions from a graphical approach. Even functions are symmetric about the y-axis. So you can see here this parabola is perfectly symmetric across the y-axis. So that's why this function is even. It's important to know not all parabolas are even. So if we graph something real quickly, just kind of freehand here, this U-shaped graph down here, it is symmetrical about a vertical line. Pardon my handwriting here. It would be symmetric about that line, but that's not the y-axis. So this function is, I'm just going to say neither, because it's not odd either. So it's got to be symmetric across the y-axis for it to be even. And that should make sense because we saw y equals x squared. That's what this graph is. Originally was even using the algebraic approach. And then finally, odd functions are symmetric about the origin. And a really easy test is to kind of flip your computer or flip your paper upside down. I'm going to do this here with this function. And when we rotate it 180 degrees, is it the same picture? Disregard all the numbers there. We're really just looking at the blue graph. The blue graph is the same. So that means this is an odd function since it's symmetric about the origin.